Hello, today we are going to solve problem 32, page 119. So we need to use this equation. The velocity is the gravitational constant, the mass of the Earth divided by the radius, 1/2. This is the equation that we got in using the centripetal force equals to the gravitational force. That's another problem that is in this series, using that F equals G M and F B squared over R. Using these two equations, we get the velocity of the satellite. But the velocity of the satellite is also the circumference around it, and that distance is 2 pi r divided by the period, the time it takes to do a complete cycle. And this is important because with these two equations we got r on the left hand side, r on the right hand side. We can solve for r and get this equation. Why is this equation important? Because if we put over here the period of the Earth is, now you know what it is, right? Period is 1 day. Well, you put it in seconds over here, 1 day in seconds over here. You are supposed to get what is called the geosynchronous orbit. So if we substitute over here the time of the Earth period, then it's a geosynchronous orbit. That means that the rotation of the satellite matches the rotation of the Earth. Remember, the rotation of the Earth is what? The definition of day, 1 day. And you need to put this in seconds. 1 day has 24 hours, 1 hour has 60 minutes, 1 minute has 60 seconds. So if you do these multiplications, you how many seconds in a day. So this is a math problem. We got r on the left hand side, r on the right hand side, and we need to do algebra to prove this equation that is very important for communication satellites. So in that case, the satellite is always pointing at the same spot on the planet. It's very important for military application and for weather application, communications, everything. So this is the gravitational constant, the mass of the Earth, the distance from the satellite to the center of the Earth. Exponent 1/2, remember that exponent 1/2 is square root. It looks like your book preferred this, so this can also be written as this. You've probably seen it like this more often than this way. First, let's eliminate the square root. So we take a square on both sides of the equation. And now the square root and the square cancel because 1/2 times 2 is 1. And on the left hand side, you get this. But on the right hand side, you get 4 pi squared r squared over t. Now you multiply by r on both sides of the equation. Over here cancel. Bring down what is left. R squared times r is r cubed. Now I need to put r by itself on the right hand side, so I'm going to multiply by the period. I'm going to divide by 4 pi squared. In that way, this cancels this. The only thing left on the right hand side is r cubed. And here, I'm going to rewrite it this way. G ME period divided by 4 pi squared. And now to eliminate the cube, you need to do exponent 1 cube on both sides of the equation. 1/3 times 3 is 1, so this cancel. And R is universal gravitation constant, mass of the earth, period, it could be any period, divided by 4 pi squared, and everything to the third power. So if this equation is very important, because if you put the period of the earth over here, it tells you what height the satellite needs to be in order to be geosynchronous. If you put over here 1 day in seconds, it will give you the altitude in meters of the geosynchronous orbit.